In the last video, we left off here. We had just set up our case 1 and case 2 for the combined gas law to compare our measurements at lab conditions to the measurements if they had been taken at standard temperature and pressure. So recall what we did was collect our gas, the hydrogen gas, over water. So we did the reaction inside the test tube. We initiate that reaction and the bubbles go displace that water, pushing down on the surface of the inside. So inside here, let me get my highlighter. So inside that contained volume, we have the water vapor plus the hydrogen, and they have to push down on the surface of that water as hard as the surface of the water has to push up against the atmosphere, that room pressure. So we'll set that total pressure inside the contained volume equal to the atmospheric pressure that we measured. We will use the known vapor pressure of water at the given temperature, which is 25 degrees, 23.8 torr, and solve for the pressure of just the hydrogen gas. We'll use that pressure of hydrogen gas to convert it from the lab conditions, right? So here we're looking at the lab conditions, and we are comparing that to the STP conditions, because then we can compare that value to our ideal gas law of 1 mole, right? So the molar volume of any gas at standard temperature and pressure is 22.41 liters per mole. So we just converted to milliliters at standard temperature and pressure by substituting in those variables. So this is the volume I would have if I had collected this at standard temperature and pressure. Okay, so the reaction we had in that test tube was magnesium metal and hydrochloric acid. So this is a good reminder for how we write chemical reactions. We need to write the phases of matter and predict our products and balance. Magnesium solid plus hydrochloric acid, all acids are aqueous, and this is going to be a single replacement where that magnesium is going to bump the hydrogen off. And hydrogen comes in its elemental form as a diatomic gas. And that magnesium is going to form an ionic compound with the chloride ions. All chlorides are soluble except with silver, lead, and mercury. So now we have to balance it, and it looks like 2 of those. We'll fix that up. Okay, now we want to calculate the number of moles of hydrogen gas produced when this much magnesium reacts. So how many moles of H2 gas react when that much magnesium reacts completely? So we'll need to cancel out grams of magnesium. And what are we looking for? Well, we will need to use a mole-mole relationship. So let's go to moles of magnesium. 1 mole of magnesium is 24.31 grams, and the grams are out of there. Then we'll need to cancel out moles of magnesium because I don't see that in the answers. What I have is moles of hydrogen. So using those coefficients from the chemical equation, that is 1 to 1. Great. So those cancel out and we end up with moles. All right, let me calculate that. So this is 1.419 times 10 to the minus 3 moles. Good to 3 significant digits. Or I could write that another way. I could say where I have the 10 to the minus 3, I could replace that with a lowercase m. So only if that's comfortable for you, you can do a conversion. Or if you're comfortable with writing it as millimoles of hydrogen, I should have my label here too. That becomes handy. Okay, so in the next part, what we need to do is calculate the molar volume. How many liters per mole using the volume we calculated in part B and the number of moles. So we measured our volume and we used the combined gas law to look at it at STP. And we know how many moles reacted from part D. And then we are going to compare that to the theoretical values of 22.41. Okay, so we had, let me write what I'm looking for. How many liters per mole did I have when we had 31.73 milliliters. Now that was good to 3 digits, but I'm going to keep an extra digit here. And that was our hydrogen gas. And we know that we had produced 1.419 millimoles of H2. So looking at those units, the millis cancel. That's just 1 over 1,000 over 1 over 1,000. So I can combine these numbers to get my liters per mole. And I get 22.36 liters per mole. All right, we would compare that to our theoretical value, the one we calculated before, which was 22.41 liters per mole at STP. So that's really close. Okay, anytime you are collecting a gas over water, which is a really good way to collect that gas, to trap it in a container, don't forget to use the vapor pressure of water. Now I'm going to go a step farther and talk about the percent difference or the percent error. That is the experimental value minus the true value or accepted value. And when we do that, we take an absolute value, so we're going to make it positive over the true value times 100%. So this is the absolute value. Those signs right there. So that means to make it positive. Make that value positive. Let me go ahead and calculate this. In our case, we have 22.36, and we'll always keep an extra digit, minus the accepted value over the accepted value, 22.41 liters per mole, and we'll keep that with 3 significant figures. Now, whenever you do a difference, remember it's a good idea to write that value. So 22.36 minus 22.41, and I get negative 0.05. Oh, this is a little different than the last time I did it. I must have rounded somewhere. That's okay, because what's our significant figure there? Oh, we don't have to worry about it yet. Times 100 times times 100%. All right, I'm going to go ahead and divide that. The negative sign, though, this we're going to use the negative sign. We will remove that with the absolute values and use the word low. Our value is lower than the true value, so that is how the percent errors work. Let me go ahead and calculate this. Divide by 22.41 times 100. 0.223. This difference is only good to one decimal place. So that's just 1. 0.2% error low. Okay. So that takes us through a review of several things we'll be doing. We'll see those percent errors in our other labs as well. So always write that difference amount, and remember the absolute value removes the negative sign. Okay, let me know if you have any questions.